This is a video recording of tests that were conducted at the Hanford site in 1966 to determine the characteristics of plutonium metal fires and means by which they can be extinguished if they did occur. The tests were all conducted in a glove box under safe conditions. The tests were actually conducted twice, the second time to videotape them because it was ascertained that no one would believe the results unless they could actually see the results. This is a result of about 2 years research conducted by Dr. Roland Felt, and represents probably the only occasion we'll have of ever seeing such tests performed. The total amount of plutonium that was involved in all of the tests was in the range of 60 to 80 kilograms. At the time, the Hanford project had discontinued the weapons program, and there was much plutonium metal available which needed to be oxidized for recovery purposes, and so the tests were provided with that material. This is the test with the ignition of a 2,000 gram plutonium metal button with a thermocouple underneath it. It's all mounted on a transite surface which is non-combustible, surrounded by a ring for safety reasons. In order to ignite this larger piece of plutonium required a carbon arc torch, doing away with the notion that large metal buttons would ignite spontaneously or with a small amount of heat. We actually had to go several minutes of heating with a carbon arc torch before the metal would ignite. Ignites, it burns somewhat like a charcoal briquette. It ignites on an edge and slowly transmits the heat to the whole button, and pretty soon the whole button is burning. This photography was taken with the lights out so that you can actually see the material as it grows. It appears as though the material is expanding, and it is, because as the metal burns, the oxide that's formed is about 1/3 the density, and so it expands, and so you have something that also appears to be something like flames, and this is actually from impurities inside of the metal. The metal itself just combines with oxygen to form oxide with no flames associated with it. The metal burns at about a temperature of about 640, 680, and then cools down to about 560 degrees and continues to burn. The black oxide material you see here is actually a mixture of oxide and metal, which will continue to oxidize over the period of the burn. Once the fire is ignited, it burns above the melting point of the metal, and consequently the metal underneath is burning with an oxide shell on the outside, and as small breaks occur in the oxide shell, oxygen gets in and you see the glow that you see here. So this material will continue to burn for about 6, 8, 10 hours with expanding and oxide. So what was a small metal button has now become a large pile of a green oxide. Some of the oxide, though, in various forms here, has a very large quantity of metal associated with it, and eventually it does go all the way to the green oxide. Here is some finely divided plutonium metal material which will ignite and burn to a temperature of about 1100 centigrade before cooling off again above the melting point of the plutonium. So all the metal turnings and pieces of metal that are associated with actually melt into a single piece. The finely divided scrap metal, of course, has a lot of surface area to unit mass. This material will ignite very easily and burn at a very high temperature. Once the ignition has occurred, though, it again melts, forms a puddle of plutonium metal with an oxide shell being formed around the outside of it, which sort of holds it intact. So that if you were to disturb this with something, it would spew metal out in all directions. This metal will continue to burn until it's totally oxide. Many of the extinguishing agents were recommended. One of them was the ternary eutectic fluoride, patented by the British. The idea being that you would be able to smother the plutonium fire by excluding the oxygen from it. This is one way of application. Unfortunately, these salts, ternary eutectic fluoride and chloride, are hygroscopic and will pick up moisture, so they have to be stored under a dry condition or in an enclosed container. By trying to smother the fire, this would exclude the oxygen. As you see here, the fire, as it progresses, there seems to be little cracks forming, so we added additional to make sure we got a really good test. Certainly that fire should have been totally smothered, and this is the result. The large cracks and fissures allow oxygen to get in. The fire is continuing to burn as if you had done nothing to it. This is simply because the small amount of oxygen required for plutonium to burn is so small that enough oxygen was actually trapped when you put the salt on the fire to allow it to continue to burn. And as it continued to burn, it formed a brittle shell which would normally exclude the oxygen, but as a result, the oxygen that got to the oxide expanded and broke that shell. This is another way of putting the metal chloride, and fluoride salts on plutonium metal fire, and as you notice, it isn't very effective, simply because as you put the bag on top of the plutonium metal, which is burning, as a molten metal, it spews out, and in this case ignited the bag. And as you remove the bag here now, you'll find that all we've done is melt a hole in the bag, and the fire is continuing to burn underneath. This may be a way of containing it, but it's not a very effective way. The plutonium metal, as it continues to burn, the salt does slow down the burning rate, in that the oxygen doesn't get to the metal quite as fast, but there's enough fissures in the salt to allow oxygen to continue to burn, allow the metal to burn. Another way of putting out a fire is to remove the heat from the fire. And so one way of doing this is to put some sort of metal powder or turnings, in this case copper turnings, on top of the fire. The copper would absorb the heat from it, hopefully lowering the ignition temperature or the burning temperature of the metal to below its ignition temperature, and once it's below the ignition temperature, the fire would go out. Unfortunately, this did not seem to work very well, in that the plutonium fire continued to burn. Certainly a lot of heat went out through the copper, because you notice that it's been oxidized, but it was not a sufficient heat removal to extinguish the plutonium metal by lowering it below its ignition temperature. There were other things such as copper powder, which might be even a better smothering agent as well as a heat removal agent. Again, this was tried, and unfortunately it did not work either. Again, there was just not enough heat removed. The fire continued to burn, and after a while all we had was oxidized copper metal powder, but the fire is still continuing to burn underneath. As you might expect, this is a big disappointment to us. We were hoping that these materials would be very effective. We even tried iron filings to see if that would be a better way of removing the heat. Again, it wasn't quite as spectacular as the copper, because it just allowed it was already black, and the fire continued to burn underneath it. The iron turnings were totally ineffective. Another way of extinguishing a fire, which has been used in several of the labs, is to use graphite powder. Graphite, again, being a good smothering agent, hopefully removing heat. One of the tests that was rather spectacular was the use of lead. We thought maybe the lead would absorb some heat by melting. Well, it melted all right, but it melted and formed an alloy with the plutonium metal and spewed out a low melting alloy. And all over our test here, and the test was terminated by using some magnetic oxide sand on it. But the graphite just was not effective. It did not remove enough heat and wasn't effective in extinguishing the fire. One of the agent that was actually recommended here and was most effective was magnesium oxide sand. The magnesium oxide sand has a tendency to cover the fire, but as the fire continues to burn, the mag oxide sand would expand with it because it wasn't fused, and as a result it actually provided a better oxygen barrier than the other materials such as other metal turnings. Magnesium oxide sand didn't remove much heat, but apparently the other materials didn't either. So the magnesium oxide sand actually turned out to be the most effective way of extinguishing a plutonium metal fire. Halon 1301 is bromotrifluoromethane. It has been used in aircraft, computer rooms, and many extinguishing techniques and applications. The application we tried to test was the application of directly putting the halon onto a plutonium metal turnings fire, as you see in the video. You also notice the video bonnet there was somewhat corroded, and you'll see why in a minute. Here we have a plutonium metal turnings fire burning around 600 to 800 degrees centigrade. As we apply the bonnet here, you notice the reaction that you get. The bromotrifluoromethane is actually decomposed into hydrofluoric and hydrobromic acid at around 2000 centigrade. The fire burned through the thermocouple, which cut out at 1800 centigrade. Estimated we went to in excess of 2000 centigrade. And so you can see that the implication here is that Freon 1301 is not effective in putting out a plutonium metal fire. However, other additional tests which were not shown on the video indicated that if you apply bromotrifluoromethane mixed with air, that had absolutely no effect on the fire. And so if you use the Freon 1301 for extinguishing normal combustible fires such as paper, trash, or wood or plastic fires inside of a glove box, application of 1301 would have absolutely no effect on the plutonium metal fire itself. And so this was quite an interesting discovery. It's only when you add the concentrated Freon 1301 directly to a metal do you actually get the material to decompose the Freon. The presence of a small amount of oxygen there, the metal has more of an affinity for oxidizing than it does for decomposing the Freon. And so this is a result which was explained in the report on the subject, but is not shown here because our video cameraman didn't feel this was a very spectacular result, and it was hard to visually film. A major concern of burning plutonium metal in a glove box is whether it would alloy with the stainless steel to form a low melting iron plutonium eutectic and consequently burn through the bottom of the glove box. These tests were run to determine this, if this was indeed the case. This was about a 600 to 800 gram quarter ingot of plutonium metal on a simulated glove box floor. The interesting thing here was that the spew of metal coming off from the side indicated that the plutonium inside, again, of course, was molten, but it spewed out onto the stainless steel floor, and the body of the plutonium continued to burn, whereas the spew was cooled enough by the stainless steel floor to go below its ignition temperature, and consequently it was extinguished, which gives you a clue as to what is the best way of extinguishing a plutonium metal fire. and that is use the glove box floor to remove the heat. The concern, of course, was whether this was going to burn through this plate of stainless steel, and certainly one test wouldn't have proven it, but thousands of burning tests have been performed in the exposing of plutonium metal by burning them in a stainless steel skillet, and in no cases have we ever found a condition in which the stainless steel would actually alloy with the plutonium metal. We followed up on many of the reported examples of rocky flats and have been able to determine that indeed, if you have a glove box situation, plutonium will not burn through the glove box. One of the big concerns also is plutonium metal in a tuna fish can, which was a standard storage can used. As the plutonium metal would burn, it would alloy with the metal bottom of the can and drip onto the next button stored below it. Much to our surprise, we found that with an ingot of plutonium metal inside of a tuna fish can which had been ignited, we found that only about half of the plutonium actually burned to oxide, and but as you notice that the plutonium had melted around the thermocouple there, but in the can itself, and this is just a mild steel can, not stainless steel, the oxide certainly accumulated in the can, but if you look at the very bottom, of the can, you'll notice it's still shiny where the metal button was actually in contact with the bottom of the can, indicating that the heat was being transferred out of the bottom of the can such that the plutonium metal never really was totally oxidized. And so the safety of storing plutonium metal in cans was much enhanced by this conclusion. In conclusion, I'd like to point out that the magnesium oxide sand indeed turned out to be the most effective way of containing the plutonium metal fire. It is not totally effective in extinguishing it. Plutonium metal will still burn underneath it, but however it provides an interesting containment so that you will prevent other materials in the glove box from igniting. So the principal concern in a glove box fire involving plutonium is to prevent the ignition of other materials such as plastic, paper, wood, anything else that will burn. And so the concern is not to put out the plutonium metal fire, because the plutonium is going to have to be recycled for cleanup anyway. The main thing is to prevent it from igniting some other source. So if you keep this in mind, this is the real message that comes out of these plutonium metal fire tests.